I pressed the button. We are moving on. We're moving on. It's in very large font, therefore it's important. Also, did not press that one. Okay. What about Megan now? Yesterday we forgot about Christine. Today we forgot about Megan. It's actually bonjour, Christine. She's in front. Okay, you're looking at her upside down. Good. Example 1. We're gonna do Parker is pumping air. No. Air into a spherical. Shh. You're my AP class. You're supposed to be quiet. Parker is pumping air into a spherical balloon. At a rate of 6 centimeters cubed per minute. What is the rate of change of the radius when the balloon has a radius of 12 centimeters? Yep. Okay. So these ones are related rates because they talk about rates of change. Rates of change, a rate of change is another way in grade 10, you talked about it, of slope, right? So a rate of change is just the same as slope. And what do we deal with slope? We deal with what? When we talk about the slopes, what do we deal with? The derivative or mean value theorem, right? We talk about those things. We talk about the slope. So, for example, it says Parker is pumping air into a spherical balloon at a rate of 6 centimeters cubed per minute. What is that? Of what? Centimeters cubed is units for volume per minute, so it's volume per time, right? So they gave us dV over dt. Why did it d? Because it's the derivative, because it's rate of change, right? And it's v over t because we have volume over time. Your units give away if it's a rate of change as well. If it's per anything, per time, it's a rate of change. So that's the first derivative. What else did they give us? What is the rate of change of the radius? So they want dr dt. When the balloon has a radius of 12 centimeters. So what does that represent? Just r. Because it's a plane unit. So we have the derivative of volume of a sphere, correct? We have the derivative of volume. So we need to have a formula to take the derivative of to get an answer. That's how related rates work. We need a formula to take the derivative of to get an answer. Okay? We need the volume of a what? Sphere formula. And on the AP exam, they'll give you like the volume formula in the question. Okay? So you can also memorize them too, just in case. But volume of a sphere is 4 over 3 pi r cubed. So we use implicit differentiation to do related rates. Because implicit differentiation is when we don't have just a variable of x or a variable of y, right? Remember when we had the xy mix, we did implicit? Same thing's going to happen here. We're going to take the derivative of v, not y. So what's the derivative of v? It's always with respect to time when it's a related rate, just so you know. The derivative of 1v is 1, and then the derivative of a v would be dv over dt. Just like when we took the derivative of a y, we did dy over dx because it was always with respect to x, and it didn't go away because it wasn't dx over dx, but the x's we didn't need to write anything because they were dx over dx. So if we had a t in here, a time, it would be dt over dt, and then it wouldn't have a derivative, right? Like we wouldn't have anything, so they would just cancel. But with related rates, you always end up with respect to time, and none of them are with time. So our volume would be, derivative of a v would be just 1, but then behind it we'd have dv over dt. Now the 4 over 3 pi is just a coefficient, correct? So when we have a coefficient r cubed, we're just going to use power rule, correct? So the 3 drops in front. 4 over 3 pi r squared. And then what do we have to remember to have? dr over dt, because we still did take the derivative of an r, correct? After we do this, we better only be missing one thing, because we want to solve for one thing, correct? And when you want to solve for something, you can only be missing one thing, and then you solve for that one thing. You do it in physics all the time. It's like out of control. I'm going to take out GCFs. It's really confusing. Okay. So, dv over dt is what? And I keep my units. Oopsies. So we get 6 centimeters cubed per minute, and I write them like this so that I can cancel my units properly. Equals the 3's cancel. 4 pi 12 what? Centimeters squared dr dt. Ultimately, in the end, dr, what's the radius measure? What's my unit? Sorry. What's my units for r? Centimeters. What's my units for t? Second. So I better get an answer of centimeters per second or I made a mistake. Minutes. Someone said it and I wrote it. Oh, and then corrected me. It made me look bad. Thank you. On this lovely podcast. Especially like the balloon animal ones. Those ones are really hard. Yeah, it's true. Start blowing the balloon up harder. Okay. So we have 6 centimeters cubed per minute equals, then this is going to be 144 centimeters squared times 4. What's that? I'm going to do this off to the side because I assumed you guys knew how to do this, but it seems as though you do not. 4 times 4, 16. 4 times 4 is 16. Oh yeah, it's not just you. It's the entire room. 4 times 4 is 16, carry the 1. 4 times 4 is 16 plus 1, which is 17, carry the 1. 4 times 1 is 4 plus 1, 576. So we get 576 pi centimeters squared dr dt. So we're going to divide by 576 pi centimeters squared. Dividing by that number is also like multiplying by 1 over that number, correct? Like, because this is a fraction over here, it'd be dividing by 576 to be on the bottom. Well, that would look weird. So if we went 6 centimeters cubed, we'll do it like this. 6 centimeters cubed per minute divided by 576 pi centimeters squared. For unit's sake, I'm going to actually go 6 centimeters cubed per minute times 1 over 576 pi. So those cancel, and I'm left with centimeters per minute, which is a good sign. And then what did that reduce to? Does 6 go evenly into 576? 6 times what goes into 5? None. 6 times what goes into 57? 9, which is? Subtract. 6 times 6 is 36. So we're going to get 1 over 96 pi centimeters per minute. So that's how fast the radius is growing. Now, if they said they were deflating the balloon by blah, blah, blah volume, right, then we'd have a negative volume. We would have to remember for the negative sign. So if you're deflating, it would be growing smaller, so you'd have to have a minus. And then your rates would be decreasing, so it would also come out as a negative. So negative doesn't mean it's so bad it doesn't exist. It just means that it's deflating or decreasing. Okay. These ones have a few different types of examples, so we're going to go through all of them. Example 2. Who do we want to use today? Beatrice is filling an ice cream cone. Get that? Because she's lactose intolerant. Actually, you know what? Beatrice and Mrs. Lepp. We both love the milk products. Yes. Is filling are filling. That doesn't make sense. We is filling. We are filling. We's filling. We hate it. Yeah, it is. When you're both lactose intolerant, it is. Okay. This could go so bad so quickly. Okay, filling an ice cream cone. The cone is 12 centimeters tall. So this is why we need 2 people. It's a massive cone, okay? That's a large cone. Yeah, we need 2 people. 12 centimeters tall and has 12 centimeters would be half of a ruler. If it's like a waffle cone, when I was making this question, I made it be big because I was thinking of those little crappy cones that are like this big that do not taste good at all. They taste like paper. Okay. The cone is 12 centimeters tall and has a radius of 4 centimeters. If you didn't catch that, that is a diameter of 8 centimeters. So it's almost equally as wide as it is tall. If the ice cream, Beatrice and I, if the ice cream fills the cone evenly at a rate of 1.5 centimeters cubed per second, what is the rate of change of the height when the height is 5 centimeters? Shh. Shh. So we know Beatrice and I are filling an ice cream cone. This cone is wonky. It's almost as tall as it is wide. The cone is 12 centimeters tall. What does that give me? That. And has a radius of 4 centimeters. So this is a ratio of height to rate of the actual cone itself. We agree? Height to radius? Cone dimensions? Yep. You have to keep reading. So it says, if the ice cream fills the cone evenly at a rate of 1.5 centimeters cubed per second, what's centimeters cubed? Volume. So what did they give me? Which is what? dV over dt, because it's a change in rate. And are they filling it? Yes, so it's positive. Now it says, what is the rate of change of the height? So they want dH dt. When the height is 5 centimeters, it would be the height of the ice cream as it's filling. It's Willy Wonka cone. Okay, so what formula are we going to use? We have dV over dt, so we're going to use the volume of a cone. So the volume of a cone formula is 1/3 pi r squared h. What's the problem with this related rate equation? Right? And we have 3 variables, correct? We don't know the radius to plug in. We also don't know dr dt. So if we keep r in here, we got super issues. Plus, we're going to have product rule, which also sucks. It's such a combination of crappiness. Okay? They did, however, give us hr, the height of the cone and the radius of the cone, which is an actual dimension between the two, right? Comparable to each other. So in this case, if they give you what the actual object's height and radius are, you can actually do a ratio of the two. So you can go radius to height. So what we're going to do is we're going to go r over h, or you could do h over r. It does not matter. What matters is that on the other side of the equal sign, if you have r on the top, you have to have the actual radius on the top. So r over h equals 4 over 12. If you went h over r, it would be 12 over 4. That's the only difference. Okay? Now, ultimately, we have nothing of r to fill in here, correct? We only have h stuff. So we need to get rid of r. So we can cross multiply and isolate for r. So we're going to cross multiply, so we're going to get 12r equals 4h. And then we're going to isolate for r so we can replace it with h's. Divide by 12, divide by 12. R equals h over 3. And now I can replace r with h over 3. We don't want to get rid of the h's. We have to take the derivative of this function. If we plug in for h, all we have left is r's, and we're in trouble. We want to plug in for r, get rid of the r's, so that we take the derivative of it. We're not having to do product rule, first off. Second off, we're doing the derivative of v's and h's, and we have answers for those. So we need the r to go the heck away, because we have nothing of help for it. If we had had all r stuff, we would isolate for h, replace the h, and then solve. Okay? So now we can take this, and we can plug it in for the r. So we're going to get v equals 1/3 pi h over 3 squared h. V equals 1/3 pi h squared over 9 times h. V equals, I can bring that 9 in front, so 1 over 27 pi h what? H squared times h. 1, H3. Now we have a formula that has only one variable, correct? So what can we do? Derivative. Differentiate it. So derivative of b is dv 1 dv over dt equals, drop the 3 in front, 3 times 1 over 27 pi h squared times dh over dt. So we get dv over dt equals 1 over 9 pi. H was this h. This is the changing h, right? So 5 centimeters. Oops, I didn't fill in for dv dt. What was dv dt? 1.5. 5 centimeters squared, and then we're solving for dh over dt, which we're hoping to get centimeters per second, right? Because height is in centimeters, time is in seconds. So we're going to get 1.5 centimeters cubed per second equals 25 centimeters squared over 9. So 25 over 9 pi centimeters squared dh dt. Then we go 1.5 centimeters cubed per second divided by 25 over 9 pi centimeters squared equals dh dt. This is technically, if you want to be all over 9, because the other ones are all over 1. So we get 1.5 centimeters cubed per second times 9 over 25 pi centimeters squared what's 1.5 times 9? 9 plus a half, so 13.5. I'll show you how to do it longhand. 1.5 times 9. 9 times 5 is 45. Carry the 4. 9 times 1 is 4. Or 9 times 1 is 9 plus 4 is 13. And then however many total decimals there are, it's how many decimal places. I only have one decimal. It'd be here. If I had 0.9 times 0.5, that would be 2 decimal places, so I'd have to do it in 2. I get 13.5 centimeters per second, and on the bottom I'd have 25 pi. If they want it better than that, they will give you the calculator section. Okay, so that's the change in height per time of the cone, of the ice cream in the cone. Okay. So now we're going to do ones that are triangles. So we have the filling ones where we fill a cone or a sphere, and now we have ladder ones. Ladder ones where you can use Pythagorean theorem and do the derivative of that, or you can use SOHCAHTOA and do the derivative of that. So this is the first one, it's the ladder question. So example 3. A ladder (8 meters long) leans against a home. if the bottom of the ladder slides away from the building horizontally at a rate of 0.75 meters per second, quickly sliding. How fast is the ladder sliding down the home when the top of the ladder is 5 meters from the ground? All right. So let's draw this out because it makes it a little easier. Here's the home. Here's the ground. Here's the ladder. Okay. I know, thanks. I worked long and hard on drawing that ladder, so. Okay, a ladder is 8 meters long. Leans against a home. If the bottom of the ladder slides away from the building horizontally at a rate of 0.75 meters per second. So that's the bottom of the ladder sliding away, right? So would that be the B equals that? What would it be? dB over dt equals 0.75 meters over second. It doesn't matter. I did B because it's base, but I often use A, B, and C anyways. How fast is the ladder sliding down the home? So that's this piece, right? So we could do height if we want. We can go dH dt equals question mark meters per second, right? When the top of the ladder is 5 meters from the ground, what did they give me? And then we could call this the ladder. So we could say L equals 8 meters. So we have 3 sides. What formula could we use? Pythagorean theorem, right? So it's going to be L squared equals B squared plus H squared. And what do we always do with the formulas when we have related rates? Derive it. So we're going to get 2L times dL over dt equals 2B times dB over dt plus 2H times BH over dt. And I told you that we can only be missing one thing. They want dH over dt. So I need to be able to fill in everything else. I can only have one unknown, right? So let's fill in what we do know. We know it's 2 times 8 meters times, we really need to know what the heck that is, equals 2b, we don't know what that is, dB over dt, 0.75 meters per second, plus 2 times 5 meters times, this is the only thing we don't know, we can't know. How can we get the other two pieces of information? So side length B. How could we get side length B when we know H and L? Pythagorean theorem. So we're going to go D squared equals 8 squared minus 5 squared. B squared equals 64 minus 25. B squared equals 39. Square root. Plus or minus, but because it's a side length, B equals 30, square root of 39 meters. So we can fill that in. Now all we need is the change in rate of the ladder. So the ladder changing in rate from meters to meters per second. This ladder, what rate does the ladder change in length as it slides down or up? Trick question. It doesn't, right? The ladder doesn't change length. It's the same length the whole way through. So this is the one that everyone sits and they're like, I can't answer this. I do not know all the information. They need to give me more. But in reality, yeah, dl over dt is just 0 meters per second because the ladder's length is not changing over time. It's a segment ladder. So this whole thing cancels. So I get 0 equals 2 times 0.75 is 1.5 root 39 meters squared per second plus 10 meters dht. Subtract that over, negative 1.5 root 39 meters squared per second equals 10 meters times dht. Divide by 10 meters. And when we're dealing with units division, you never go over top of a fraction. You always write it. So we're going to get negative 1.5 square root 39 meters squared per second times 1 over 10 meters. Negative 0.936 meters per second. So if they wanted into this, they'd have to let you a calculator. Why is it negative? Because it's sliding down the wall. So you have to remember that if the volume is decreasing or if the side length is decreasing or something like that, then you would actually have to use a negative, right? Or get a negative. Okay, we have one more. Example 4. I said if you're getting that answer, they'd have to allow you a calculator. Okay, you are looking at the New York ball drop on New Year's Eve. Yep. At a distance of 100 meters away from the base of the structure. If the ball drops at a constant rate of 2 meters per second, what is the rate of change of the angle between you and the ball when the angle is pi over 4? Hint, you're going to use tan. Try it out. So we're going to get tan theta. Wow, forgot to press the thing. Equals y. I didn't do anything, literally. I just rewrote the equation. But you have theta. Theta is pi over 4, my friend. Pi over 4. All right. We understand this part, right? We got this? Okay. Then we need to do the derivative of it. So we're going to get derivative of tan is secant squared theta d theta over dt equals the derivative of y over 100 is this is the same as 1 over 100 y, right? Okay. So it'd be 1 over 100 dy over dt. And the change in rate is what? Secant squared pi over 4, which is the same as secant pi over 4 squared, right? And then this is, what was the change in rate? 2 meters. Ball drops. Yeah. Now, pi over 4 is root 2 over 2, root 2 over 2, correct? So cos of pi over 4 is root 2 over 2 cx. So secant of pi over 4. Pi over 4 is 2 over root 2. We agree? So secant of pi over 4 equals 2 over root 2. But I don't want secant of pi over 4. I want secant squared of pi over 4. So it's going to be 4 over 2, which is 2. Yes, that scared me that you guys took a little while to reply to that question. So we're going to get 2 d theta over dt equals negative 1 over 50 meters per second. It's dropping. The sky, literally, dropping. Well, that sounds like a you problem. All right, so then we're going to divide by 2. And technically, you could say rads, meters per second. Oh, it'd be rads per second, not meters per second. This has a meter on it. Rads per second. That's one of the easier related rates, actually, because there's not a lot of extra stuff. Page 248, numbers 12, 13, 17, 20, 23. And what I want to make sure that you can do is these types. So even if you redo these ones. Okay, so these 4 types are the big 4 types, and then the max and min word problems, and then on Friday you're going to have just those. Okay.